All right, this is the practice exam for chapter 4 to 6. Don't forget that we also did chapter 3, which is like electron configuration and quantum numbers. So that's going to be on there as well. Keep in mind, this isn't your test, right? This just gives you a general idea of some topics I could throw on there. So just don't think if you're going to succeed on this and learn this really well, that's going to help you. You need to learn each individual topic, understand why each thing or each answer is what it is. So I'll start with this first question. It says, give a possible molecular formula for C3H5ClO. This is already the what we call empirical formula. It's the most reduced formula that we can have. And so the potential molecular formulas would be maybe 1 times all these coefficients, or excuse me, subscripts, or 2 times these subscripts, or 3 times these subscripts, etc. So for example, if I multiply all these subscripts by 1, I'd get C3H5Cl, the same thing, right? If I multiplied them by 2, I'd get C6H10Cl2O2. Or if I multiplied them by 3, I'd get C9H15Cl3O3. So it's looking for a couple things here. It's looking to see if you understand that Cl and O are different, and also that you understand that if you multiply one subscript, you have to multiply them all. So these are all potential molecular formulas. And of course I could have gone on and done times 4 times 5, etc. But the answer is already here. I think I see it right there. It is C. That would be 2 times. All right, the next question. Give the name for SNO. So on the periodic table, even though SN is over here, it's under our little separation over there. So we don't know its charge. We do know the charge of things over here in the 1 plus column. We know things in the 2 plus column. And we know that aluminum's 3 plus, gallium's 3 plus, indium's 3 plus, zinc is 2 plus, cadmium, I always switch those, you know that, and then silver is positive 1. So 3, 2, 1. Outside of the first column and the second column and those, we don't know the charge, we have to use Roman numerals. So here I see tin and oxide. Oxide is in the 6th column, it's got a -2 charge over here. So no, oxygen is going to be 2 minus. So our question is, what must tin be? Well, it must be 2 plus, has to be. And that's why when we go to write it, it's tin, 2, oxide. You need to know the endings. You know the difference between eights, ites, etc. And B was our answer. All right, let's look at this next one. I kept with tin just so we can see the difference. But here again, it's tin, so we don't know the charge. So we know we're going to have to write the charge in Roman numerals, and we also have to figure it out. Well, we know sulfate is SO4 2 negative. If you don't know that, go see polyatomic ion video. I think it was week 5. Week 4 or 5, and learn how to memorize those. Okay, so sulfate is SO4 2 minus, and there are 2 of them, and therefore tin must be positive 4 in order to cancel that out, and that's why tin 4 sulfate is your answer. Next, give the name for HNO2. Well, we know NO3 negative is nitrate, but this is NO2 negative. That's nitrite. Do you remember, if you ate the ick, you got the itis. So ates will become ick and ites will become us in naming acids. And that is why this acid, which is H with NO2 with a nitrite, is nitrous acid. Give the names for this. I told you in class, that name didn't even exist. But we should recognize that it starts with an H, so it's an acid. All your options would have been acid, so we can assume it's aqueous. But then it says, next we have to kind of figure out what it is. Remember, H2SO4 is sulfuric acid. If we have an oxygen, we don't use hydro. So if we don't have an oxygen, we do use hydro, and that's why this is hydrosulfuric acid. So no O, hydro. All right, let's keep on moving. Okay, question number 6. What is the chemical formula for chemical name, for S2O? Here we have nonmetal. In fact, they're both nonmetals. And because they're both nonmetals, that's when we can use the di, tri, tetra, etc. We can use those prefixes when they're both nonmetals. Again, on the periodic table, just in case you've missed something, which can screw you up the whole time, these are metals. And up there on the upper right are nonmetals. And hydrogen. So we have 2 sulfurs and 1 oxygen. This is just disulfur monoxide. The rule with monoxide is we just never use mono at the very beginning. We can use di, tri, etc. We just never use mono as the very first thing. If you just say sulfur, for example, monoxide, I would assume you have just 1 sulfur. All right, now we're getting this one. How many oxygen atoms are contained? A few of you had a question because you got slightly different numbers than this. It just depends how many numbers you used, but if I provide it for you, I suggest you use it and save your time. Though, of course, I get that you're trying to practice, so that never hurts. All right, so in this case, we've got grams, and we want to turn it into atoms. So we've got to go from grams to mole to molecule to atom. And don't be surprised if I ask you a question that goes the opposite direction. Okay, so we are going to start with 47.6 grams. I don't have enough space to write it, but this is aluminum carbonate. And we know that there are 233.99 grams per mole of aluminum carbonate. So we've made it to mole town. Now we need to go from mole to molecules. Well, we got to put mole down here, and we got to put molecule up here. And the relationship between those two things is that there is 6.022 times 10 to the 23rd molecule in a mole. All right, now we made it to molecule town. Now we just need to get to atom town. We know a single molecule of this Al2CO3, and then it's got 3 of them, has how many oxygen atoms? Just to break this down, because I see this a lot. This is what this would look like: 2 aluminums and then 3 carbonates. That's, each carbonate is a carbon with 3 oxygens on it. So it has a total of 9 oxygens in one single thing. If you calculate that out, you get an answer of D. So 47.6 times 6.022 times 10 to the 23rd times 9 divided by 233.99. Everything on top divided by things on the bottom. Let's move on to this next one. We've got phosphorus and chlorine. It gave us a certain amount. You actually didn't matter what units you started with. The ratios would have worked out if you just pretended those were grams. But nevertheless, let's go ahead and work it out the way we were given. So the first things first, we know that milli is equal to times 10 to the negative 3rd, right? So for phosphorus, we have 10.15 times 10 to the negative 3rd, which would be equal to 0.01015 grams. And chlorine, the same thing. that milli is equal to times 10 to the negative third. In other words, we've got 34.85 times 10 to the negative third grams, just to write it out. And so this would be 0.03485 grams. All right, what do we do with grams every single time? We turn it into moles. So using the molar mass of phosphorus from the periodic table, taking grams, I'm going to divide it by the 30.97 grams per mole it has. And I made this line way too big. This gives me an answer of 0.000327774. I'm going to do and that would be mole. I'm going to do the same thing down here. Divide this by 34.45 grams per mole. And I made the same mistake, and this is 0.00098307 mole. In other words, if we were to actually write this out, I'm going to draw down here a little bit. If we were to actually write this out, it would be phosphorus 0.003277, chlorine 0.00098307, but we need to get a whole number. And so what we do to get a whole number is you divide each one by the smallest number. I think you agree that 0.03 is the smallest number. And what this does is this gives me 1, and this gives me 3. Now, if this had been 1.5, we would have had to multiply them both by 2, but it's not. It's whole numbers. It's CL. It's P1 CL3, which is totally cool. Look at me, I did a CL up there too. So PCl3 is your answer. Okay. Now choose the bond that is most polar. They're going up and to the right of the periodic table. Things become more electronegative. We're excluding the noble gases over here. But if you zoom in on this column right here, it goes like this: fluorine, chlorine, bromine, iodine. And so the most electronegative element is fluorine, and polarity has to do with the biggest discrepancies between two things, the biggest difference in electronegativity. So fluorine wants electrons way more than iodine wants electrons, and therefore it will create a more polar bond. Choose the best structure for ICl5. There's a few different ways we can go about this. I would look at formula charges though. Formula charges are valence minus sticks minus dots. The overall charge for ICl5 is 0. So what that tells you is most likely, most stable structure will have formula charges all equal to 0. Remember that all the formula charges in a thing have to add up to equal the overall charge of the compound. The overall charge is 0, therefore maybe we can find a structure there where the formula charges are all 0. All right, chlorine and iodine, they're both in the 7th column, so they both have 7 valence electrons. Both of them. Again, because they're in the 7th column. Okay, so you can just go around and look and see valence minus sticks minus dots for each one. So for example, if I look at this one right here, let's start with this chlorine right here. I've got 7 valence minus 1 stick minus 6 dots. And that gives me a formula formal charge of 0, which is great. And that means this one would be 0, this one would be 0, this one would be 0, anything with a single stick and the 6 dots. But then I get here, it's a double bond. So if I calculated the formal charge of this chlorine, it would be 7 minus 2 sticks minus 4 dots, which would give me positive 1. And positive 1 is not 0. I hope you agree with that. And then even if I looked at the iodine now, I have 7 minus 1, 2, 3, 4, 5, 6 dots, or 6 sticks, 6, 0, excuse me, minus 0 dots gives me a positive 1 as well. So if this is positive 1 and that's positive 1, there is no way that this structure can be correct. Why? Because the overall charge would be positive 2, and we know that's not the case. We know it was neutral. So you can move on to the next ones, or you can just take a hint from the pattern that when it was single bonded, a chlorine with 6 dots, it had a formula charge of 0. So I would immediately go through and get rid of anything that had a double bond to chlorine. That one, that one, that one. That leaves us only this one, but let's double check and make sure it's right. Again, the formula charge for each of these chlorines would be 0. Anything, again, that looks like this has a formula charge of 0. And then we have our iodine down here. Let's go ahead and calculate it out. We have 7 valence, minus 1, 2, 3, 4, 5 sticks touching it, minus 2 dots touching it, gives us a formula charge of 0. Therefore, this one absolutely makes the most sense. All right, number 13, I'm asking you for the SO bond order for sulfate. First, we gotta draw sulfate. We can draw sulfate very quickly. Why? Because we know it's got a 2 negative charge. Oh, sulfite. I'm glad I looked at that. Sulfite. Okay, we can draw it relatively quickly. Why? Because we know the formal charge of an oxygen that looks like this, a single bonded one, has a formal charge of -1. If it's double bonded, it has a formal charge of 0. So here, with a -2, that tells us that there are probably going to be 2 of these single bonded things. And so let's draw them out. If we draw it real quickly, single, single, and then 1 of those oxygens must be double bonded. Cool. And then if we look at the formal charge of sulfur here, remember, once we've drawn all these formal charges to match, then we can look at sulfur and fix it. So right now it has 6 valence minus 4 sticks minus how many dots to equal 0? The answer is 2, and that's why I put 2 on it. And now it has a 0 formal charge. If you need help with this, watch any of my drawing Lewis structures videos. I think I have drawing Lewis structures quickly. And that walks through how I'm doing what I'm doing right now. All right, but that's not even the answer. The answer is, we'll figure it out. The question is about bond order. In other words, how many bonds are between sulfur and oxygen? Well, here we have unequal sharing because this has double bond and this has a single, and that just doesn't actually happen. Instead, this bond right here is delocalized and shared equally among all 3 of these. So I think you would agree they all have at least 1, and then this one that is shared between 3 things would be 1/3 for each one. That's why bond order is 1 1/3. All right, number 12, we can use what we know from up here to draw this very quickly. It's BrO4 negative. What that tells us is we're going to draw Br, and one of those oxygens must be single bonded. That's going to be our -1 formal charge. The rest have to be double bonded. Does that look crazy? Heck yeah, it does. But does it matter? Well, if this is a -1 formal charge, and now this bromine is 7, has 7 valence electrons, minus 7 sticks minus 0 dots equals 0. So this is 0, all these are 0, and that's -1. That's one of the most stable structures you can actually make. And so that is why that's our stable structure, because it asks for the best Lewis structure. This would be our best. And our formal charge again for bromine would be 0, because we had to calculate it to determine if it was the best structure. All right, on to our last page. says, determine the electron geometry and molecular geometry of NCl3. All right, so N, by the way, is in this second period. So remember that all these things that can have more than an octet are N equals 3 or below. So more than octet, that's only for N equals 3 or below. So when you see nitrogen, usually to me that's a red flag because that's N equals 2. That means this dude must have an octet. And that's okay because I can't imagine that you're going to run into a situation where you're trying to put more than an octet on nitrogen. And so we would just do it the way we did it before. Chlorine, chlorine, chlorine. We add everything. We fill in. Oops. This is supposed to have 6 dots on this chlorine. Sorry, I got a little carried away with that dot. And on the nitrogen. So now we have 1, 2, 3, 2, 4, 6, 7, 8 things on nitrogen and 8 things on everything else, and everything has an octet. But you want to make sure when we're not looking at formal charges that you ensure that it has the correct number of valence. So nitrogen is in the 5th column, it has 5, plus 3 times 7 for each chlorine, so that's 21, 26. So she have a total of 26 electrons. Let's go ahead and count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We are good. So this is our most stable structure. Now we can answer the question. So determine the electron geometry and the molecular geometry. You are just going to straight up have to either understand molecular geometry or memorize the table, which is actually relatively simple to memorize. You just draw a whole 0, 0, 1, 2, 3, 4, and then there's just look at the table. Figure out a way to memorize it. You guys can do that. I have a lot of faith in you. But when we go to do this, I like to just have a better understanding of it rather than just memorize it. And so these are 4 groups that are trying to get away from each other as much as possible. That's like when I stood in class and I put my hands in the air and then I twisted the top torso, my torso. This is tetrahedral electron geometry. So electron is tetrahedral. Again, because it has 1, 2, 3, 4 electron groups. But its molecular geometry is essentially what it looks like without one of those electron groups. And it would result in what kind of looks like a pyramid. I don't know what I'm doing or why I'm doing it. No, don't even, Keegan. It would be like, douche, 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 kind of like I already drew it. There, that's a little better. All right, so it kind of looks like a pyramid, right? And if we kind of ignore these, and that's why it is trigonal pyramidal and tetrahedral. All right, last but not least, this one. And I did see a few people have some trouble with this one, but ask yourself, if this is n equals 3 or greater, we can go ahead and use the formal charge rules to build it. So let's do it. We got Xe, let's put 4 F's on it. Give all of those F's an octet, they're n equals 2, so they need an octet. And now look at xenon here. If we calculated its formal charge right now, it would be 8 minus 4 minus 0 equals 4. And that tells you it needs 4 dots on it. So it must have 4 dots. This is the correct structure. And essentially what it looks like is it's like an X. And then up on top, it has a lone pair, and on the bottom, it has a lone pair. So this lone pair is on top, and this lone pair is on bottom, and it's all within a plane. Its electron geometry has 1, 2, 3, 4, 5, 6 things around it. So its electron geometry is octahedral, so it's one of those 2 things. But then its molecular geometry, only looking at that X-looking thing, is square planar because it's in a plane and it looks like a square. This would be our only option that works, but let's look at the hybridization. It's S, P, 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 D, 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 D. And then we say we've got 1, 2, 3, 4, 5, 6 electron groups around it. So we say 1, 2, 3, 4, 5, 6. And I went through an S, I went through 3 Ps, and I went through two D's in order to get that. And that is why C is definitely your answer. And yeah. All right, guys, study hard. Do the worksheets. Go back, do your homework again if you want to, whatever's going to help. And I will see you in class on Tuesday for the next practice exam. Bye.